In mathematics, a diffeomorphism is an isomorphism of smooth manifolds. It is an invertible function that maps one differentiable manifold to another such that both the function and its inverse are smooth. Definition: given two manifolds M and N, a differentiable map F. Mn is called a diffeomorphism if it is a bijection and its inverse F-1. Nm is differentiable as well. If these functions are r times continuously differentiable, F is called a CR diffeomorphism. Two manifolds M and N are diffeomorphic if there is a diffeomorphism F from M to N. They are CR diffeomorphic if there is an r times continuously differentiable bijective map between them whose inverse is also r times continuously differentiable. Diffeomorphisms of subsets of manifolds. Given a subset X of a manifold M and a subset Y of a manifold N, a function f xy is said to be smooth if for all p in X there is a neighborhood um of p in a smooth function g un such that the restrictions agree. F is said to be a diffeomorphism if it is bijective, smooth and its inverse is smooth. Local description. Model example: if U, V are connected open subsets of Rn such that V is simply connected, a differentiable map F. UV is a diffeomorphism if it is proper and if the differential dfx Rn is bijective at each point x in U. First remark: it is essential for V to be simply connected for the function f to be globally invertible. For example, consider the realification of the complex square function, then f is surjective and it satisfies thus. Though dfx is bijective at each point, f is not invertible because it fails to be injective equals f. Second remark: since the differential at her point is a linear map, it has a well-defined inverse if and only if dfx is a bijection. The matrix representation of dfx is the n times n matrix of first-order partial derivatives whose entry in the ith row and jth column is. This so-called Jacobian matrix is often used for explicit computations. Third remark: diffeomorphisms are necessarily between manifolds of the same dimension. Imagine F going from dimension n to dimension k. If n less than k, then dfx could never be surjective, and if n greater than k, then dfx could never be injective. In both cases, therefore, dfx fails to be a bijection. Fourth remark: if dfx is a bijection at x, then f is said to be a local diffeomorphism. Fifth remark: given a smooth map from dimension n to dimension k, if df is surjective, f is said to be a submersion, and if df is injective, f is said to be an immersion. Sixth remark: a differentiable bijection is not necessarily a diffeomorphism. F equals x3, for example, is not a diffeomorphism from R to itself because its derivative vanishes at 0. This is an example of a homeomorphism that is not a diffeomorphism. Seventh remark: when F is a map between differentiable manifolds, a diffeomorphic F is a stronger condition than a homeomorphic F. For a diffeomorphism, F and its inverse need to be differentiable. For a homeomorphism, F and its inverse need only be continuous. Every diffeomorphism is a homeomorphism, but not every homeomorphism is a diffeomorphism. F. Mn is called a diffeomorphism if, in coordinate charts, it satisfies the definition above. More precisely, pick any cover of M by compatible coordinate charts and do the same for N. Let phi and psi be charts on, respectively, M and N, with U and V as, respectively, the images of phi and psi. The map psi f phi-1 uv is then a diffeomorphism as in the definition above, whenever f psi-1. Examples: since any manifold can be locally parametrized, we can consider some explicit maps from R2 into R2. We can calculate the Jacobian matrix. The Jacobian matrix has zero determinant if, and only if xy equals 0. We see that F is a diffeomorphism away from the x-axis and the y-axis. Where the n are arbitrary real numbers, and the omitted terms are of degree at least 2 in x and y. we can calculate the Jacobian matrix at 0. We see that G is a local diffeomorphism at 0 if, and only if, i.e., the linear terms in the components of G are linearly independent as polynomials. Let we can calculate the Jacobian matrix. The Jacobian matrix has 0 determinant everywhere. In fact, we see that the image of H is the unit circle. Surface deformations in mechanics, a stress-induced transformation is called a deformation and may be described by a diffeomorphism. A diffeomorphism F UV between two surfaces U and V has a Jacobian matrix dF that is an invertible matrix. In fact, it is required that for P in U, there is a neighborhood of P in which the Jacobian dF stays non-singular. Since the Jacobian is a 2 times 2 real matrix, dF can be read as one of 3 types of complex number: ordinary complex, split complex number, or dual number. Suppose that in a chart of the surface, the total differential of U is, and similarly for V. Then the image is a linear transformation, fixing the origin, and expressible as the action of a complex number of a particular type. When is also interpreted as that type of complex number, the action is of complex multiplication in the appropriate complex number plane. As such, there is a type of angle that is preserved in such a multiplication. Due to dF being invertible, the type of complex number is uniform over the surface. Consequently, a surface deformation or diffeomorphism of surfaces has the conformal property of preserving angles. Diffeomorphism group. Let M be a differentiable manifold that is second countable and Hausdorff. The diffeomorphism group of M is the group of all CR diffeomorphisms of M to itself, denoted by diff or, when R is understood, diff. This is a large group, in the sense that, provided M is not zero-dimensional, it is not locally compact. Topology. The diffeomorphism group has 2 natural topologies, weak and strong. When the manifold is compact, these 2 topologies agree. The weak topology is always metrizable. When the manifold is not compact, the strong topology captures the behavior of functions at infinity and is not metrizable. It is, however, still bare. Fixing the Riemannian metric on M, the weak topology is the topology induced by the family of metrics as K varies over compact subsets of M. Indeed, since M is sigma compact, there is a sequence of compact subsets knots whose union is M. Then, the diffeomorphism group equipped with its weak topology is locally homeomorphic to the space of CR vector fields over a compact subset of M. This follows by fixing a Riemannian metric on M and using the exponential map for that metric. If R is finite and the manifold is compact, the space of vector fields is a Banach space. Moreover, the transition maps from one chart of this atlas to another are smooth, making the diffeomorphism group into a Banach manifold with smooth right translations. Left translations and inversion are only continuous. If R equals infinity, the space of vector fields is a Frechet space. Moreover, the transition maps are smooth, making the diffeomorphism group into a Frechet manifold and even into a regular Frechet Lie group. If the manifold is sigma compact and not compact, the full diffeomorphism group is not locally contractible for any of the 2 topologies. One has to restrict the group by controlling the deviation from the identity near infinity to obtain a diffeomorphism group which is a manifold. See Lie algebra. The Lie algebra of the diffeomorphism group of M consists of all vector fields on M equipped with the Lie bracket of vector fields. Somewhat formally, this is seen by making a small change to the coordinate x at each point in space. So the infinitesimal generators are the vector fields examples when M equals G is a Lie group. There is a natural inclusion of G in its own diffeomorphism group via left translation. Let diff denote the diffeomorphism group of G, then there is a splitting diff G times diff, where diff is the subgroup of diff that fixes the identity element of the group. The diffeomorphism group of Euclidean space Rn consists of 2 components, consisting of the orientation preserving and orientation reversing diffeomorphisms. In fact, the general linear group is a deformation retractive subgroup diff of diffeomorphisms fixing the origin under the map FF T in diff sigma. Here diff 0 is the subgroup of diff that preserves all the components of M, and sigma is the permutation group of the set pi 0. Moreover, the image of the map diff sigma is the bijections of pi 0 that preserve diffeomorphism classes. Transitivity for a connected manifold M. The diffeomorphism group acts transitively on M. More generally, the diffeomorphism group acts transitively on the configuration space CKM, if M is at least two-dimensional. The diffeomorphism group acts transitively on the configuration space FKM and the action on M is multiply transitive. Extensions of diffeomorphisms in 1926. T. Barredo asked whether the harmonic extension of any homeomorphism or diffeomorphism of the unit circle to the unit disk yields a diffeomorphism on the open disk. An elegant proof was provided shortly afterwards by Helmuth Nesser. In 1945, Gustav Choquet, apparently unaware of this result, produced a completely different proof. The diffeomorphism group of the circle is pathwise connected. This can be seen by noting that any such diffeomorphism can be lifted to a diffeomorphism f of the rails satisfying f equals f plus 1. This space is convex, and hence path connected. A smooth, eventually constant path to the identity gives a second, more elementary way of extending a diffeomorphism from the circle to the open unit disk. Moreover, the diffeomorphism group of the circle has the homotopy type of the orthogonal group O. The corresponding extension problem for diffeomorphisms of higher dimensional spheres Sn-1 was much studied in the 1950s and 1960s, with notable contributions from René Thom, John Milnor and Stephen Smale. An obstruction to such extensions is given by the finite abelian group gamma n, the group of twisted spheres, defined as the quotient of the abelian component group of the diffeomorphism group by the subgroup of classes extending to diffeomorphisms of the ball Bn. Connectedness for manifolds. The diffeomorphism group is usually not connected. Its component group is called the mapping class group. In dimension 2, the mapping class group is a finitely presented group generated by den twists. Max Den and Jacob Nielsen showed that it can be identified with the outer automorphism group of the fundamental group of the surface. William Thurston refined this analysis by classifying elements of the mapping class group into three types: those equivalent to a periodic diffeomorphism, those equivalent to a diffeomorphism leaving a simple closed curve invariant, and those equivalent to pseudo-Anosov diffeomorphisms. In the case of the torus S1 times S1 equals R2, Z2, the mapping class group is simply the modular group SL and the classification becomes classical in terms of elliptic, parabolic and hyperbolic matrices. Thurston accomplished his classification by observing that the mapping class group acted naturally on a compactification of Teichmuller space, as this enlarged space was homeomorphic to a closed ball. The Brouwer fixed-point theorem became applicable. Smale conjectured that if M is an oriented smooth closed manifold, the identity component of the group of orientation preserving diffeomorphisms is simple. This had first been proved for a product of circles by Michel Hermann. It was proved in full generality by Thurston. Homotopy types. The diffeomorphism group of S2 has the homotopy type of the subgroup O. This was proved by Steve Smale. The diffeomorphism group of the torus has the homotopy type of its linear automorphisms, S1 times S1 times GL. The diffeomorphism groups of orientable surfaces of genus G greater than 1 have the homotopy type of their mapping class groups. The homotopy type of the diffeomorphism groups of three manifolds are fairly well understood via the work of Ivanov, Hutcher, Gabay and Rubinstein, although there are a few outstanding open cases. The homotopy type of diffeomorphism groups of n manifolds for n greater than 3 are poorly understood. For example, it is an open problem whether or not diff has more than two components, via Milnor, Kahn and Antonelli. However, it is known that provided n greater than 6, diff does not have the homotopy type of a finite CW complex. Homeomorphism and diffeomorphism. Unlike non-diffeomorphic homeomorphisms, it is relatively difficult to find a pair of homeomorphic manifolds that are not diffeomorphic. In dimensions 1, 2, 3, any pair of homeomorphic smooth manifolds are diffeomorphic. In dimension 4 or greater, examples of homeomorphic but not diffeomorphic pairs have been found. The first such example was constructed by John Milnor in dimension 7. He constructed a smooth 7-dimensional manifold that is homeomorphic to the standard 7 sphere but not diffeomorphic to it. There are, in fact, 28 oriented diffeomorphism classes of manifolds homeomorphic to the 7th sphere. More unusual phenomena occur for 4 manifolds. In the early 1980s, a combination of results due to Simon Donaldson and Michael Friedman led to the discovery of exotic R4s. There are uncountably many pairwise non-diffeomorphic open subsets of R4, each of which is homeomorphic to R4. And also there are uncountably many pairwise non-diffeomorphic differentiable manifolds homeomorphic to R4 that do not embed smoothly in R4. F. Second remark: since the differential at her point is a linear map, it has a well-defined inverse if and only if dfx is a bijection. The matrix representation of dfx is the n times n matrix of first-order partial derivatives whose entry in the ith row and jth column is. This so-called Jacobian matrix is often used for explicit computations. Third remark: Diffeom is a diffeomorphism if it is proper and if the differential dfx Rn is bijective at each point x in U. First remark: it is essential for V to be simply connected for the function f to be globally invertible. For example, consider the realification of the complex square function, then f is surjective and it satisfies thus. Though dfx is bijective at each point, f is not invertible because it fails to be injective. In mathematics, a diffeomorphism is an isomorphism of smooth manifolds. It is an invertible function that maps one differentiable manifold to another such that both the function and its inverse are smooth. Definition: given two manifolds M and N, a differentiable map F. Mn is called a diffeomorphism if it is a bijection and its inverse f-1. Nm is differentiable as well. If these functions are r times continuously differentiable, f is called a CR diffeomorphism. Two manifolds M and N are diffeomorphic if there is a diffeomorphism f from M to N. They are CR diffeomorphic if there is an r times continuously differentiable bijective map between them whose inverse is also r times continuously differentiable. Diffeomorphisms of subsets of manifolds. Given a subset X of a manifold M and a subset Y of a manifold N, a function f xy is said to be smooth if for all p in X there is a neighborhood um of p in a smooth function g un such that the restrictions agree. F is said to be a diffeomorphism if it is bijective, smooth and its inverse is smooth. Local description. Model example: if U, V are connected open subsets of Rn such that V is simply connected, a differentiable map F. UV is